Hello, AP Chemistry, and welcome to an introduction to acids and bases. In terms of sections, this should cover 16.1 and 16.2. So, first of all, we talk about the definition of Arrhenius acids and bases, which you should know, and which you should also recognize. The reason that we don't commonly use that, right, is that it's too limiting, right? It is too specific, and it doesn't include enough species, right? Which brings us to the Bronsted-Lowry definition, which is going to be our operating definition. The end of your book, I think it's section 1611, talks about Lewis acids and bases, which is probably the most broad definition of acids and bases, and applies to things that are also not aqueous. Since 99% of what we talk about is aqueous to some extent, right, Bronsted-Lowry works just fine. Okay. One of the key things to Bronsted-Lowry definition of acids and bases, right, is that we get the idea of conjugate pairs, right? Now, here you need to memorize this definition, right? A Bronsted-Lowry acid is something that, ding, 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 right, has a proton to donate, which means that if we're looking at a set of species and trying to decide what to do with them, right, if we want to call something an acid, it needs to have a proton to donate, okay? Bronsted-Lowry definition of a base is, right, something that can accept a proton, which by extension, in terms of its structure, means it has to have a lone pair, right? Which is where structure is important, because going back to what we talked about before, a lot of our models and a lot of our representations won't necessarily show lone pairs, right? Something like this, for example, right? This, right, doesn't show that this nitrogen has a lone pair, right, when we see this written formula. But we should know, because we should be able to doodle out the Lewis structure, right, that yes, that nitrogen has a lone pair, which means this is capable of accepting a proton, right? Structure, really important. So, in terms of our conjugate pairs, let's say that we have an acid that we're going to symbolize this way, right? And that acid, oh, that's not how I want to do that. That acid, in conjunction with water, has the ability to do this. Yes? In that, basically now we are talking about reactions with water, right? Wherein we have our aqueous acid, our liquid water, forming this and this. Yes? So if we talk about our conjugate pairs, right, this is an acid, right? And its conjugate is its deprotonated form, right? So this would be its conjugate base, right? The deprotonated form. Whereas if this is an acid, kind of like redox happens in a pair, if this is our acid proton donor, this must be our base or proton acceptor, with this being its conjugate acid, right? The protonated form, yes? Where again, the definitions are the same, right? The acids are the protonated forms, the bases are the deprotonated forms, and the pairs are the pieces that go together, yes? So for example, it would not be okay to say that this is our acid and this is its conjugate base, right? Because that's not true, right? This is not a pair. They don't rotate around the same thing, right? Okay, so then if we want to talk about, for example, a base, right? So we should say that we have a base plus water, right? And that's going to give us, again, the definition of a base is it accepts a proton, right? So we have Hb, and if it accepts a proton, its charge is going to go up by 1, right? Plus the hydroxide ion, right? Which means that here we have a base, and so we would be looking over here at the other version of it, and this would be its conjugate acid, yes? Right? By extension, if this is a base, this must be acting as an acid, and this must be its conjugate base, yes? Fantastic. All right, note the use of arrows in the middle. Right here, we're just doing forward arrows, which would imply there's no equilibrium, though that really depends on what we're talking about, right? Right. Clarify later. All right, so write the formula for the conjugate acid. So when we say conjugate acid, what do we mean? What's an acid again? Right, the acid is the, what? Protonated form, right? Acids are the protonated form, because if we go back one, right, acids, right, acids are the protonated versions of their base components, right? So here, what we're really talking about is what's the protonated form of each of these, right? So if we add a proton to this, right, that becomes H2SO3. What happens to my charge if I add a proton? Right, neutral. If I add a proton to this, right, neutral. If I add a proton to this, right, 2 minus. If I add a proton to this, right, yes? All right, now let's talk about from the other point of view. Let's say that instead we were asked to write the conjugate base for each of the following. Now, what would that mean? Right, we would be looking for the deprotonated form, yes? We'd be looking for the deprotonated version of each of these. Now, if I were to deprotonate this, what would that look like? Yes? All right, can I deprotonate this? No. Can I deprotonate this? No. No. Which is why the question asks for acid, right? But that's what it means, right? So it's really important that we are really comfortable, right, with the definition of a Bronsted-Lowry acid and base, and then it's just a matter of applying it, right? All right. Next up, when lithium oxide is dissolved in water, the solution turns basic. If it turns basic, that means we have increased the amount of hydroxide. So we have our lithium oxide ion with water. Do be mindful anytime we're talking about something reacting with water, that's also known as a hydrolysis, okay? When something reacts with water to make something that's new on the other side, right? That's referred to as a hydrolysis, okay? So write the equation for this reaction and identify the conjugate pairs. So if I have O, 2 minus, plus water, what am I going to make? Right. It's a base, right? It's acting as a base, which means that it's going to, ding, 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 right, take a proton and make that, yes? Which is why this is a decidedly basic ion, right? Because we're not producing just one, we're producing 2 hydroxides from the course of this reaction, yes? So for one of these, we have basically double the effect on our pH, yeah? Okay. Let's say that again. Double the effect on our hydroxide ion concentration, which then has an effect on the pH. Okay? All right, next up. Pairs and what it means when something's acidic or basic. So if we take a look here, right, this is from your guys' textbook, and here we have our strong acids. Okay? Now, if something is a strong acid, by definition, what does that mean about it? Right, dissociates completely. Right? Which means that for any one of these, if I said HCl plus H2O, right, I would just use a forward arrow, right, and I would say H3O plus Cl minus, okay? Just a forward arrow because they're strong acids, okay? Now, if I were talking about any of my weak acid species, like for example, if I want to talk about H2S, I would say this plus water, and then here is where it would be appropriate to do that plus my deprotonated form. Yes? Makes sense? Okay. Now, a couple of things to take note of, right? So this table is all full of conjugate acid-base pairs, okay? So if we take a look, right, we see that, so for HCl, its conjugate base is Cl minus, right? If we came down here and we were talking about this as a base, right, this would be its conjugate acid, yes, so forth and so on, right? Now, things to take note of here, right? We have our strong acids, we have our strong bases. Now, when something is a strong acid, we say that its conjugate base has negligible basicity, okay? Negligible basicity. If something is a strong acid, its base, its conjugate base, doesn't really act basic, okay? If something is a strong base, its conjugate acid does not display any acidic tendencies, right? And note that this is tiny, tiny portion, tiny, tiny portion. What makes up the most of this table, though, is our weak species, right? So what that means, though, by extension, is that for any of these weak acids, its conjugate base is actually basic to some extent, right? Which is going to make up a huge section of our thinking exercises for this chapter, basically, right? Which means that if I have some HF in solution and I have F minus in solution, I'm going to have to be really, really thoughtful about whether or not my solution is acidic or basic. Yes? Because both of these species have the ability to act, right? Acidic, right? Or basic. So anyway, important stuff to know. And like I said, we're going to delve into this a whole lot more during the course of this chapter. Make sure you know these definitions really, really well. Thank you for listening. Be good and stay tuned for the auto-ionization of water. All right. See you later. Bye.